Okay, so for the video lecture for this week, we're going to tackle another chapter. So it's the fourth chapter. It's the chapter that we call a root locus. So in order to start this chapter, root locus is completely new chapter. Just to remind you, the chapter that we had previously. In chapter 3, what we had was the analysis of time response of different system, and we have tackled basically the notion of stability, right? And we have basically understand how do we determine whether a system is stable or unstable. But now in this fourth chapter, it's not just about uh, determining whether the system is stable or not stable. What we need to do is as well is to basically to improve the response of the system. So now we are in the case of stable system, but what we need to do is to improve the response of the system. So for example, in chapter 3, we have seen different criteria of performance of system of first order and second order. For example, one of the criteria, some of the criteria of performance of this time response are, well, that includes the time constant, the rise time, the steady state error, and for example, things that are related mostly to time constant, which are rise time, settling time, and so on, right? So in this chapter on root locus, what we're going to do is we're going to modify the system, basically adding what we call a corrector uh, to basically improve the response of the system, right? So in order to improve it, there is different method that we can use, and root locus is one of them. That's the easiest to understand, and that will allow you to basically to overview the range of different character that you can use in order to improve the system, but without making it unstable, right? So in order to do that, at the end, what I hope that at the end of this chapter, what you will be able to do is the first one is to understand the control system problem. So in root locus, what we're going to see is that we will have a problem related to adding a character that will need us to therefore use root locus. So, and then in order to use root locus, what you need to do is we will go through a certain revision on the vector representation of complex number. So at the end, you should be able to master the vector representation of complex number in order to use root locus. And thirdly, once we've done that, you will be able to define the root locus of a system, right? And finally, you will be able also to understand the properties of root locus on different systems, right? So this chapter, we will have a few videos lecture on this chapter, and I hope at the end you will be able to understand fully, grasp the concept of root locus and use it in application. So we'll go to the first part, which is basically to understand the problem of control system. So we have seen that we will have a different type of response. Let me have my pointer first. So we know that depending on the systems, we will have different type of response, and then in those responses we will have basically different criteria of performance, and those criteria of performance could include settling time, rise time, or percentage of overshoot, and etc. etc. Right? So depending on the specification, we might want to have one system or another. For example, here we have a system in blue, the response in blue, red, green, a blue, a light blue or cyan, and then a magenta, right? And in this different response, they actually comes from the same transfer function, but it is just added with a certain constant. So let's say imagine until now what we have had is basically a transfer function that looks like this, but k will be equal to 1. So it's 1 over s multiplied by s plus 2. So we can see that it is a second order time response, right? So what we can do is, let me have my pen back, if I may. So usually what we had previously is basically a system with, let's say, 1 over s multiplied by s plus 2. And here I'll call 1 as k, right? So we have now our transfer function as k over s multiplied by s plus 2. And imagine if we can change the value of k. So k is a coefficient. We can have it whether it could be equal to 0.5, it could be equals to 1. So if it is 1, we have exactly this transfer function. It could be equals to 2, and it could be equals to 15. And we see that this is basically the plot of the step response. And we can see that as k changes, the time response also changes. So it can goes from, for example, here, the system is basically over damped. It can goes into a critically damped position, and then it goes into under damped position, where we can start to see a percentage of overshoot, and it start to oscillate, right? So depending on this value of k, we can remark that basically the time response changes, and we can have a system which is basically over damped, critically damped, or under damped, right? So what we can do therefore is basically we can isolate this k from this transfer function. So now it becomes k multiplied by gs. And what is gs? Gs is basically 1 over s multiplied by s plus 2. So what is interesting here? The thing that is interesting here is that by changing the value of k, imagine if we have a hand that we can tweak the value of k. Depending on the value of k, we can change the response of the system. So depending on the specification of the response, so for example, if you're working for a system that need a very quick response, you would basically want your system to have the response like in magenta, right, over here, but it will have overshoot. For example, if you have so this is a very fast response, but with overshoot. For example, if you have a specification, for example, if your company want you to design a control system, a system that responds without any overshoot, so this would be your system. So this is a system with no overshoot. But of course, you understand that the consequence will be the system will respond slower than the system with overshoot. So depending on the value of k, by adjusting the value of k, we can have different response. So what we need to do as an engineer in control system, you'll take the specification of the system, and you'll try to change this value of k so that your time response will correspond to the specification demanded to you, right? So what is root locus? So root locus is basically, it is a graphical representation. It is a method that we will learn here, which consists of a graphical representation of the closed loop system. So the whole system, the closed loop poles as a system parameters k is varied. So it is a representation of the poles in the closed loop as the parameters k is varied. So imagine if we change the value of k from 0 to infinity, we will have a graphical representation on S-plane, the position of the poles on S-plane of the closed loop as k varies from 0 to infinity. So that's what root locus is. Root locus is basically a graphic, a tracing on S-plane of the position of the poles. So you have many positions, right? If you have only 1k, if you have only 1k, then you have only one position. But if you have multiple value of k, let's say k1 until kn, you will have n position. Therefore, you have a tracing, a plot on your S-plane of the possible position of the poles, right? So by using that, it is basically a powerful method that will allow you to analyze and design a system, and you can oversee basically the stability and the transition response of the system as well. So that's about the introduction, what root locus is and why do we use it. So now let's tackle the... So now we have understood from previous slide that root locus is actually about identifying the pole's position as the value of k's of our constant that will multiply with the transfer function is varies. As k varies, we want to identify the pole's position. So there's another problem related to it. So let's see here. So in general feedback control system, so this is just a repetition what we had previously. Imagine we have k, the coefficient that we multiply with our transfer function gs, right? So k, sometimes we call it as character, or we can call it as we could call it as character or controller. and then we have GS, our transfer function, and then we have HS, the feedback transfer function, right? And then what happened is there is two type of transfer function that we can have here. The first one is what we call open loop transfer function. So I get my pointer. So the first one is what we call open loop transfer function. Open loop transfer function, or also called loop gain, is easy. It is basically the transfer function on the forward side. So you have K GS forward side multiplied just by the feedback. So KGS multiplied by HS, that's what we call loop gain or open loop transfer function. The open loop transfer function without the feedback is just a straight line KGS multiplied by HS. But when you want to identify the transfer function of the complete closed loop system, that's not what we want. The thing that we want to evaluate is the closed loop transfer function. So what is the equation for the closed loop transfer function? The equation for the closed loop transfer function, by now you all understand, it is the first section of the second chapter. We have looked into it. When we simplify, what we need to do is basically to simplify it and find an equivalent transfer function that will have the same input RS, the same input output CS. So we'll end up with a transfer function of K multiplied by GS over 1 plus K GS HS. So this is the closed loop transfer function that we want to study, that will allow you to find the position of the poles of the closed loop system. Because now we have a closed loop system. In order to study its stability and study its response, we need. So now we have the closed loop transfer function. The question is it easy to find the position of the poles? So is it easy to find the position of the poles? It is easy to find the position of the poles for GS, but now it is a closed loop, so it's a much complex system. It's KGS over 1 plus KGS HS. So poles location, we can see that the poles, of course, it will depends on, the poles will depends on the denominator of our transfer function. And on the denominator of the transfer function, we can easily see that there will be multiple number of position of poles. There will not only single position of poles, there will be multiple position of poles depending on the value of K. Because we said just now, what we can have, basically, we can tune and tweak the value of K so that the response of the system will change. If the response of the system change, it means the position of poles also have also changed. So poles location varied with the gain. So we call this gain, I'm sorry, I called it controller just now, but now as it is a constant, we can call it as a gain. So as the gain value changes, the poles location also changes. So let's find out the open loop and closed loop transfer function. So it is not useful to find the open loop transfer function, but now it's just to show you basically so that you understand the complexity of finding the poles location of the closed loop transfer function. So for the closed loop transfer function, basically to find the poles, basically you have to, what you have to do is to develop everything. So we know that GS, what happened here is, I'll walk through this. It is very simple. It's just, it looks like a lot, but there's nothing much in here. GS is basically the transfer function, and the transfer function, we know that the transfer function have a numerator and a denominator. So now it splits GS into numerator of GS, denominator of GS. The same goes for GS and HS on the bottom, on the denominator. So here we have numerator of GS, denominator of GS, numerator of HS, and denominator of HS, right? So if you do all the development until the end, you'll end up with this particular equation, right? So we know that finding the poles of the closed loop means finding the poles of basically the denominator. So the denominator now becomes DGS, DHS plus K, NGS, NHS. So we have K, so the position of the poles will vary, will change as K changes, right? So we can see it's a complex terms, and it's not easy to identify quickly, just like in open poles, in open loop. If it was in open loop, KGS means at the denominator we will just have the denominator of GS multiplied by the denominator of HS. So here it is a certain polynomial, but it is not as complicated as this, and certainly doesn't depend on the value of K. But this is not what we want. The thing that we want is this here, over here. Let me take my pen. So the thing that we want to evaluate is the term on this denominator that will allow us to find the pole's position, and we can see that it depends on. So now if we continue the comparison, so basically, so I'll go very quickly through this. Right, let me get my pointer back. So in open loop it's fairly easy, DGS, DHS. In closed loop is pretty lengthy. So let's concentrate on closed loop. So in closed loop, it is a combination of numerator and the denominator. So we can see here there's numerator, there's denominator, and the poles also depend on k. So it is fairly complex. Alright, so therefore with closed loop system, the poles are not easily obtained and change with the value of k. So it's root locus that will allow us to plot the position of these poles that changes with the position So here let's take a look at an example. So imagine if you have a forward transfer function of gs equals to s plus 1 over s multiplied by s plus 2. And let's say we have hs, the feedback transfer function of s plus 3 over s plus 4. And of course, let's say let us draw the closed loop first so that you understand it. So imagine you have basically you have k, the gain. It will be multiplied by your gs transfer function. So here is the output cs. Here you have a comparator that will compare the signal from the feedback. So the transfer function of feedback is hs, right? And then here you have your input of rs. So gs is this transfer function, and hs is this transfer function, s plus 3 over s plus 4. So if we just study the open loop, you'll have k s plus 1, s plus 3 divided by s plus 2, s plus 4. If you want to identify the pole's position of this transfer function, we can see it's equals to 0, minus 2, and minus 4. It's fairly easy. But this is not the one that we want to find, because when we study a closed loop system, we want to study the totality of it. So you need to find the poles of the reduced system, right? So the reduced, let's say I call it as G1S, and G1S is, of course, it's k gs over 1 plus k gs hs, right? So for closed loop system, I'm sorry, I have written on this part, but I think you can still see it. So for closed loop system, we can see if you do the development of the equation. Let me take my pointer back. You can see that you will end up with this equation, the transfer function of closed loop system. At the denominator, you will have s plus 2, s plus 4. So this is basically the denominator of our g and h, but you will also include basically the numerator of g and h, which is s plus 1, s plus 3, and you will include k as well. So what we can see is that now the poles of our closed loop system, what we have is it also depends on k. So I think by now you have completely understand the usage of this root locus. So root locus will allow us to find the poles position of the system, the range of position of the poles of our system as k varies, right? So basically here we don't know what's the value of poles. We know that there's one, there probably one at 0, minus 2, and minus 4. 0, minus 2, minus 4. But here it will be minus k and minus 3k. So this k and this minus k and so now that's the first part about understanding the problem of a closed loop transfer function. And if you want to basically the system to respond properly, we need to identify the pole's position as our gain changes. So let's go to the next part, to the next section, which is the revision on vector representation in complex number. So here in this second section, we're going to revise a bit on the notion of complex number. So basically, it's why do we do this? Because let me have my pointer. Sorry. So basically, because our position of our poles S is basically a complex number, right? It is a number that is situated in a complex plane with a real term sigma and a complex term j omega. So j is the axis of the imaginary axis of the complex axis. So we have a real plus an imaginary part, right? So that's why we're going to revise the notion of complex number and the representation of vector in it. So complex number is basically just a vector. So for example, S, it is a vector situated in the S plane with two axes, the first one being the real axis and second one being the imaginary or what we call complex axis. So imagine if we have a number of S which is equal to sigma plus j omega, it is a vector that looks like this. It starts from 0, so it has a vector means it has a certain magnitude m and a certain direction theta. So theta or the angle or direction is in reference to the axis sigma, and magnitude m is basically the length of this vector s. So for example here this vector x s has the length in sigma axis of sigma and the length in j omega axis as j as omega. So what is the magnitude and the direction theta of the vector s? The magnitude is basically you do the Pythagoras theorem. So it's the length of sigma square plus omega square root. So that's how you find the length m of the vector. And theta or the direction of the vector, how do you find theta? So theta is basically this angle between sigma and the vector s. So the angle, this angle theta is basically, if you look at this triangle, it is what do we call it? I got it on the tip of my tongue. It is a right it's a right triangle. So you have basically theta. If you do tangent of theta is basically omega divided by sigma. So if you want to find theta, then it means theta is basically arctangent or the inverse tangent of omega over sigma. So if you have a complex number, in order to what you can do is, because the written in complex number is pretty complex, we can also write it in another term, which is a representation of the vector. And the representation of a vector is written like this: S equals to the magnitude, and then you put a symbol of angle or direction, and then you put the angle of theta. How to find m? So you have this equation here, Pythagoras theorem. And how do we find theta? Theta is just the arctangent of the vector. So omega over sigma. Omega is the j omega axis, sigma is the length on the real axis, right? So if we have a complex number, this is the representation in vector. Again, why do we do this? Because basically your position of poles in S. So what happens if S is a variable in a function? How to represent the complex number? So for example, imagine if you have a function fs equal to s plus a. So imagine fs being your transfer function, right? So this is equivalent of having a transfer function equals to s plus a, and s, we know that s is your position of poles, and position of poles of course can change, and the position of poles is a complex number of sigma plus j omega. So what happens if s is a variable in this function? So let's see. So we know fs equals to s plus a, it's given, and we know that s is a complex number of sigma plus j omega. So what you do is basically just replace s with your complex number, which is sigma plus j omega. So you would have fs equal to sigma plus j omega plus a, right? So at the end, you end up with your transfer function fs. So now it's not a transfer function, it's the location, the answer of your transfer function at s equals to sigma plus j omega. So now it's equal to sigma plus a plus j omega, right? So it is another complex number. It's not just sigma plus j omega. Now it's sigma plus a plus j omega, and it is a function. fs, right? So graphically, if you want to plot it, so basically previously we have sigma plus j omega, it's somewhere in here. So now it's added with a, so the length in sigma axis is extended to here. So now this is the new vector of fs, which is sigma plus a plus j omega, right? So now let's have a look at this, another example. So this is what we had previously, which with fs equals to s plus a. So let me write first. So what we had was the function given to us was fs equals to s plus a, and we know that s equals to sigma plus j omega. So if we have only s, which is sigma plus j omega, this is the vector representation. But now if s is a variable in fs, which is s plus a, therefore we have sigma plus j omega plus a. So our new presentation of fs, the representation of fs is just like this. So we have j omega on the j omega axis, and on the sigma axis now we don't have just sigma, it's sigma plus a, right? So fs is sigma plus a plus j omega, and it is also the same representation as this. Basically it's the same vector. The vector of fs, this and this are exactly the same. The difference is just that now we have here, what we have is the origin of the vector is placed on 0, 0, but now we can also move it at minus a, so that it end here at just sigma. The two vectors are the same, it's just placed at different. So let's take an example. Imagine if we have a function of imagine if we have a complex number. So this is a complex number, right? A complex number of s equals to 5 plus j2. So how do you plot it? So imagine this is an example. So s, this is s, which is 5 plus j2. So this is a vector s. So imagine if this s is now plugged into a function of fs s plus 3. So fs now has become, so we replace s with 5 plus j2. So now we have, in real axis we'll have 5 plus 3, plus in the complex axis or imaginary axis j2. So we'll end up with fs equals to 8 plus j2, right? So 8, if we look at here, we have 8 plus j2. So this is our new vector fs. So s is just this black vector, fs is this new red vector, right? So it's s in the function f. But it is also the same vector as this one. If we move, so previously we had the origin of the vector at 0, but we can also move it if we want to have it pointed to the same location. What we need to do is just to shift it to minus 3 on sigma axis, so that it will end up at 5 in sigma axis. So we have this vector now that starts at minus 3, 0. It is the same vector. It is the same vector, right? Which is fs s plus 3. So fs equal to s plus a is also a complex number and can be represented by a vector drawn from the 0 to the function, or from the 0 of the function to the point s, right? So it can be drawn like this as well. Okay, so now so that is the thing that we've seen previously was the graphical representation, but what we want to do at the end is, we know that the fs that we're talking about here is not any function. This fs is basically what is going to be our gs, which is our transfer function. And gs, for example, if fs was just s plus 2 or s plus 3, our transfer function is not in this form. Our transfer function will have a numerator and s divided by denominator ds. So it is a much more complex number, complex or vector. So we need to know how to represent our function gs, or here is written as fs, in the vector representation as well, right? So vector representation. So let's see this. So this might look complex, but later we will dissect the equation and we'll try to do an example of it. So the function fs consists of the first one, this one is the numerator of s and the denominator of s. So here is the symbol of basically a product. So it's a product of different terms s plus zi, and at the denominator is the different term of s plus pj. So I is basically the number of terms that you have on the denominator. J is the number of terms that you have on the numerator, on the denominator. I'm sorry. So how do you find if you have a if you have a function that has a fraction like this, which is typically the case of our transfer function gs? How do we find? The question is, how do you find m and how do you find theta? So m, how do you find m? M is basically the product. So we know that on top we'll have 0, at the bottom we'll have the poles, right? So M is basically the product of 0 divided by the product of poles. It's the product of 0 divided by the product of poles. And what about theta, or the angle? The angle is basically the sum of 0 angles minus by the sum of poles angles. So if we have a fraction, basically we have the fraction is numerator s over denominator s. So what we call 0 here is this. So this is 0. This is poles, because we know that from numerator that we deduce 0, and from denominator that we deduce the poles. So if we want to find the angle, is the angle of 0 minus the angle of poles. And the angle of each 0 and poles basically is the sum of angle of 0 minus the sum of angle of poles, right? So if you don't understand this, let's tackle an example. So imagine we have now our function fs. So now it's written as fs, right? So we have basically 3 terms. We have s plus 1, s, and s plus 2. So fs is basically a combination of 3 functions, s plus 1, of 3 terms, s plus 1, s, 1 over s, and 1 over s plus 2. Let's say the position of poles that we're interested in is s equals to minus 3 plus j4. S equals to minus 3 plus j4. So how the question is here, again to make it clear, we want to, what is m of fs? What is theta of fs? So that we can represent fs in the representation of m, vectorial representation of magnitude and angle. Okay, let's do this. So what is fs? So we have the 3 components of fs. So the first one is, so let's say the first one, let me change the color of the pen first. The first one is s plus 1. Where is s plus 1? S plus 1 is over here. S plus 1, what we need to do is basically we replace s with minus 3 plus j4. If we replace minus 3 plus j4 in s, what we have is minus 2. So this one will become minus 2 plus j4. And we see that over here, it's the representation of s plus 1. It's minus 2. If we look here, between minus 1 and minus 3, we have minus 2. And here we have plus j4. So this is the representation of the first term. Let's go to the second term. The second term is s. So where is s? We have s over here. So why is it being represented by this vector? Because s have been replaced with minus 3 plus j4. So s is just minus 3 plus j4. If we look at here, between this point and this point over here, we have minus 3. And here again, we have plus j4. So this is the representation of s. And finally, where can we represent s plus 2? Let me change the pen. So s plus 2, if we replace s with minus 3 plus j4, we will obtain basically minus 1 plus j4. This will become minus 1 plus j4. So it is s plus 2 is over here. Why is it over here? Being represented by this vector is because here we have minus 1, and again here we have plus j4. So now you have basically to make it clearer, what we have over here is basically the vector representation of this term that make fs, right? This term that make fs. So these are the components of fs, right? So if we want, what we need to do next is basically what we do here is to write the vector in vector representation. So let's say now it's done for s plus 2, right? How do we get this number? So if you look at s plus 2 is minus 1 plus j4. So how do we find magnitude of s plus 2? Magnitude of s plus 2 is basically, it's 1 square. So we take this term. If you look at the vector, is the length of sigma is 1 square plus length of j omega is 4 square root. So we get square root of 17. That's where we get the square root of 17. And what about the angle? If we look at the triangle built by this vector, if I redraw the vector here, s plus 2, we will have basically, not s plus 2, it is, I'm sorry, it's minus 1 plus j4. We will have minus 1 over here, and we will have 4 over here. The angle that I want to find is basically this angle theta, right? Because the vector is like this is the angle theta. This angle theta, what is it? It is basically 180 degree minus arc tangent of 4 divided by 1. So if you do 180 minus arc tangent of 4 divided by 1, you will basically obtain 104 degrees. So that's how you get the representation, vector representation of s plus 2. So let me erase all the writing that I have over here so that you can see it clearer. So now let's see what are the vector representation of each vector, the writing in this form, m and magnitude and direction. So for s, if you do the calculation, you get square root of 20, and the direction is 116.6 degree. And for s plus 1, for s, you'll get the representation in vectorial form. The magnitude is 5, and the angle is 126.9, right? So those are the three components. If I get my pen back. So these are basically the three components of the vector fs written in the form of m, magnitude, and direction. So what is fs? Fs, of course, is the combination of three of them. So fs is basically, in terms of magnitude, so it's the magnitude of s plus 1 divided by the magnitude of s multiplied by the magnitude of s plus 2. And what about the angle? The angle is basically the angle of s plus 1 minus the angle of sum of s and s plus 2. Basically, this is just like if you're having plus here, but in parentheses this, right? So this is the sum of s and s plus 2, their angles, and here you have the angles of s plus 1. So it's the angle of s plus 1, which is the numerator, minus the angle of the denominator. So if you do the calculation, you'll get at the end fs written in the form of magnitude and direction of the vector. It will be equal to 0.217 with the direction of minus 114.3 degrees. So that is the location of fs, or the vector of fs, if you have your s equals to minus 3 plus j4. So that's all about the revision on complex number the vector representation of complex number, and the combination of them if you have a function with multiple terms. So please revise that because we'll be using that in root locus. So next, let's go to the section of defining and constructing root locus. So now we're getting into the core of the topic matter, which is root locus. So before that, let's take a look at the textbook definition of root locus. So root locus is a graphical representation of the closed loop poles as a system parameter is varied. It is a method that you use to analyze and design control system for stability and transient response. So it was invented by W.R. Evans. So in order for us to basically understand and start to define root locus, we'll do this through an example. So imagine if you have basically a lens, or imagine a telescope that you need to point to a certain location, a certain position. So this is in the case of a camera, right? So it is basically you in the system you have the transfer function of the motor and the camera. Imagine it's a simplified transfer function. It is basically equals to K2 divided by S multiplied by S plus 10. And what we have in front of it, we will have a certain gain, K1. So in real application, this gain is what we call basically amplifier, because it amplifies and make our system respond quicker. Is what we call amplifier. And in this case, the amplifier have a value of K1, which is a real number, right? A real number, of course, with a certain range. We'll see later. And then it is a closed loop, because why do we have closed loop? We have closed loop because we want to control the position of the camera. We have in the input the subject's position, and in the output we want it to have a certain camera position. So let's look at it. So what we need to do first is, of course, to simplify the closed loop transfer function, to find basically an equivalent transfer function, a single transfer function that represents the whole closed loop. So if you do the calculation, to get that it will be equals to K over S square plus 10S plus K. So now we use just K, with K representing the product of K1 and K2. K1 and K2. So now what do we do next? We know that we have a transfer function of K over S squared plus 10S plus K. The input is RS, the output is CS. What we want to know is basically the position of poles as K varies. So that's what root locus is. Imagine if K varies. So here what happened is, we'll take a few sample of value of K's. We'll try this value of K's. I encourage you to try and test it on your own to get the feel of basically manually doing root locus, because later we'll use MATLAB just to find root locus, to trace root locus. For this different value of K, we'll find the position of poles for our closed loop system. So now, if we look at our closed loop system, it's a fairly simple closed loop system basically. It is a second order transfer function, right? If you have a second order transfer function, that means how many poles will you have? You will have two poles, so there will be pole 1 and pole 2. So you'll be calculating pole 1 and pole 2 with different value of K. For example, here what happened is they have a range, so they propose a range of value of K ranging from 0 to 50 with a step of 5. So 0, 5, 10, so on until 50. So you will calculate for each value of K this pole's position. So you know how to calculate the pole's position. It's just the root of this polynomial, right? So you have, for example, you see that as K varies, the position of poles also varies. For example, in the first half up to 20, both poles are real numbers. But in 25, what happened is the poles start to be, it is a real number, but the poles are located at the same position at -5. And then as you increase K, what happened is the poles will start to have complex component. It is now a complex number, right? So what we're going to do in root locus is basically we're going to plot this position. We're going to plot this pole's position. So we will start, for example, with K equals to 0. If K equals to 0, the pole is at -10 and 0. So it's located at -10 For k equals to 0, it's minus 10 and 0. So it's these two black points. If we increase, for example, let's go to k equals to 20. If k equals to 20, the poles position equals to minus 7 and minus 2. So it's minus 7 and minus 2. Minus 2 point something. Close to 3, right? So we see that if I get my pen, change it to red. So we can see that as k increase, what happened is pole's position move in this direction. It start at 0 and it moves toward the center. As k equals to 25, what happened is both poles are located in this position. So basically the poles move towards the center, and then as you change k equals to 30, what happened? It will equals to minus 5 plus j2 minus 5 minus j2. So you will have basically minus 5 is over here, plus j2, you have this point and this point. So the poles, basically it moves, the two poles move towards each other to meet at 5, and then it starts to separate in this direction. And if you increase it more towards 50, what happens is the poles will continuously grows toward infinity on positive and minus direction. Basically what will happen is if you increase k more, it will continuously grow the position of the poles to plus j omega and minus j omega. So these lines that I'm plotting here, so there are basically two poles position, therefore there are two lines. Let me get another color. So let's say the first pole is 0. This is one position of root locus, one tracing of root locus, not position, one tracing. And this is another tracing of root locus. So what it means is basically the position of poles moves following these blue and yellow lines as k increase. So this is what we call the trace or the plot of root locus. So now in this section of the video lecture, we're going to study the properties of root locus, right? So you're going to see if a transfer function, if a point is on the root locus, what kind of properties does it have, right? So let's start with the transfer function of the closed loop. So we know by now that this is a transfer function of the closed loop that we want to study in our root locus in order to be able to trace and plot our root locus. And then, so how do we get the poles of this closed loop? We know that we get the poles by studying the denominator of the system. So the denominator of the system is 1 plus gs hs, gs being the forward transfer function, hs being the feedback transfer function, right? In order to find the poles, we want the denominator to become 0. So if we move 1 to the other side, it means that kgs hs equals to minus 1, right? So before we go to this statement, so kgs hs, we've seen in previous slide, what is kgs hs? So kgs hs is the part of the transfer function that we call open loop gain or open loop transfer function, right? This is the open loop gain. Let me write it down. So we call this part kgs hs. When we did the comparison with the closed loop transfer function just now, we call this as open loop gain or open loop transfer function, right? So if we want to get the poles of a closed loop, we want that the open loop gain equals to minus 1, right? So that is the simple way to put it. If you want to study the poles of a closed loop, it is equals to studying the open loop gain, which is kgs hs, but now not equals to 0, equals to minus 1. Okay, so now let's take a look at this function. In this function, kgs hs equals to minus 1, we know that a transfer function, just like what we've seen just now in Fs, this transfer function is a complex number, right? It is a complex number. It's not just simply 1 minus 1, a real number. It is a complex number. So, so the value minus 1 is, in fact, a complex number. So KGS HS equal to minus 1. It means that if we have it in a vectorial notation, it means that the magnitude is 1 and the angle is 180 degrees, right? The magnitude is 1 and the angle is 180 degrees. Because in our complex plane, in our complex or S plane, what we can see is minus 1 is located on this side, right? The vector of minus 1 is this particular vector. And how do you write it in vectorial form, where we have a magnitude and a direction? The magnitude is 1. The magnitude is 1. Well, magnitude is without any signs, right? It's always positive, the magnitude. So it's 1. And the direction is 180 degrees. So this is basically the notation of KGS which is the open loop transfer function in vectorial form. So the magnitude, what is the magnitude? Again, the magnitude is 1, and theta, the direction, is 180 degrees. So it is what is this term here, 2k plus 1? So what 2k plus 1 means, actually, for if you look at here, 180 degrees, we can have 180 degrees at any repetition. For example, if k equals, take a k integer of 0, 1, 2, 3, right? So let's say if I write down, so k is basically for k equals to an integer of 0, 1, and up to any number that you would like. Imagine if k equals to 0, it means it's 1 times 180. If k equals to 1, then it means the angle is k equals 1. It means 3 times 180. What it means is basically 1 rotation, 2 rotation, and 3 rotation. So it's the third rotation. So we fall again at 180 degrees. Because what happened is a transfer function may have many poles, right? So for example, here this transfer function, this forward transfer function of KGSHS, if it only has 1 poles, it means k will be equals to 0. You will only have 180 degrees as the direction. But imagine if you have 2 poles, what happens? If you have 2 poles, means that you will have 2 angle, and the 2 angle is of course for k equals to 0 and 1. For k equals to 0 is 180 degree, and for k equals to 1, it will be equals to 3 times 180 degrees. So we will always place in this direction. So this is basically the properties of root locus. So in root locus, we have 2 main properties on transfer function, right? So the first properties that we've seen just now in previous slide is what we call magnitude condition. So in terms of magnitude, in a root locus, if k, we have k in a transfer function, on a root locus, what happened is our forward transfer function, or I'm sorry, it's not forward, the open loop transfer function of KGSHS is equals to minus 1, right? Because the pole's location is when 1 plus KGSHS equals to 0. So on a root locus, KGSHS equals to minus 1. And what does it mean, this minus 1? Minus 1 means it's a vector of magnitude 1 and with an angle of 180 degrees. So there are 2 conditions. The first one is related to, let me have my pointer. So the first condition is related to the magnitude, and the second condition is related to the angles, right? So the first condition is related to magnitude. So in terms of magnitude, the magnitude of KGSHS is equals to 1. What does it mean? It means that if the magnitude of KGSHS equals to 1, that means that your gain K is equals to 1 over the magnitude of GSHS. So we may find the value of our gain K by this formula of 1 over the magnitude of GSHS. So that's the first condition on magnitude. And then the second condition, which is on the angle. What's the condition on the angle? On the angle, we know that the angle should be 180 degrees. because to find the poles is equals to -1. -1 is a complex number, means the angle is 180 degree. So the angle of our function, of our open loop transfer function, KGS HS, will be equals to 2k plus 180. So 2k plus 180, with k being an integer from 0 to, of course, infinity. So k will depends on the number of poles that you have. So for example, if your if your open loop transfer function is a function of a third order, it means you will have 3k of 0, 1, and 2. If it is of order of 4, then you have 4k from 0, 1, 2, and 3, and so on and so forth. So beware of these two conditions. So if a point is on the root locus, it means your k will be equals to 1 over the magnitude of the forward transfer function. I'm sorry, it's not forward transfer function again, of the open loop transfer function. And the angle condition, the angle of your forward of your open loop transfer function will be equals to 2k plus 180, right? Okay, so let's to be so imagine so the condition that we need to take into account is basically there are two conditions, right? So the conditions are on angle and on the magnitude and angle, and those two conditions can be summarized in this only one equation, KGS equals to -1. If you know that this -1 is a vector, then it means that you know that the condition is magnitude equals to 1 and the angle equals to 2k plus 180 degrees. So this is the only thing that you have to bear in mind. So imagine if you're given with a unity feedback system forward transfer function. So unity feedback system forward transfer function. So this is basically your open loop transfer function. So you give directly the open loop transfer function. So if you have, for example, in your problem or in your exercise, a block diagram, what you need to find out is find this KGSHS. So imagine what's given here, GS here is basically, it is GS, but we have a unity feedback. Unity feedback means, what does it mean? Let me draw. So it actually means that you have K, you have GS. So this KGS is this. The K is integrated directly into GS, but your feedback transfer function is basically just 1, right? So it is just 1. So if you want to find the open loop transfer function, KGSHS, it is also equals to this GS. So you don't have to do any manipulation whatsoever. This is already the transfer function that you're going to study in this root locus for this particular case, right? If you have a more complex block diagram, then you have to reduce or join something and then recalculate the open loop transfer function. Okay, so what does this example ask us to do? The first question that it asks is, let me get my pointer back. The first question that it asks is this point, so that's this particular point, minus 3 plus 0j, so this is 1 point, right, is on a root locus. Is this point, minus 3 plus 0j, is on a root locus. So what does it mean? It means that it also asks you that is this point, minus 3 plus 0j, is a poles of this open loop transfer function. Is this the poles of this open loop transfer function, right? You understand it, right? Because if this point is on the root locus, it means it is the poles of this open loop transfer function. And then secondly, it asks us if the point is on the root locus, so mean if the point is one of the poles of the transfer function, find the value of k. So what is the value of k when we are on that particular point on our root locus, right? So how do we do this? So the first thing that you need to do, so these are the steps. Let me erase this first. Get my eraser. So the first step that we need to do is to determine zeros and poles of the forward transfer function. We need to determine zero and poles of the forward transfer function. And then we need to determine, so basically determine zeros and poles. Determine, it also means that determine the numerator and denominator of the transfer function. In second step, we have to determine the angles from zeros and poles to the interested points. So we need to determine the angles. Which angles? Angles from zeros and poles. So we have zeros and poles to the interested point. What's the angle from zeros and poles to the interested points? And then thirdly, we will have to determine the length of the vector from zeros and poles to the interested point. And number 4, add all angles. If it is equals to multiple 180, then the point is on the root locus. So this is basically application of the condition on angles. And then number 5, finally, determine k using length of zero and pole vectors. So at the end, we will be able to determine the value of k using the length of zero and pole vectors. So this is basically the condition on the magnitude. So let's see how do we do this. So the first thing that we need to do in the first step is determine zeros and poles of the forward transfer function. So we have, of course, as usual, you can use whatever method you want, but of course the usual method that we use, you can basically just key in your calculator directly, because we know that our transfer function is a second order transfer function. It's a quadratic equation. The polynomial is of order of 2, so you can use this quadratic equation. So remember, this quadratic equation is only for transfer function with of second order. So our GS was k multiplied by s plus 2 over s squared plus 4s plus 13. So you might be confused, it is GS. It's not just GS. This GS is also the open loop transfer function. It's also the KGSHS, as I mentioned in previous slide. So please be careful with that. So if you use the quadratic equation or you key in your calculator, what you get is you get two poles, right? The first pole is at minus 2 plus J3, and the second pole is at minus 2 minus J3, right? So the two poles are complex number. So if we plot them, there is one at minus 2 plus J3 and another one at minus 2 minus J3. And here we also plot the zeros. So where is the zero? So we have determined the poles. Now what about the zeros? The zeros is on the numerator. We can see that the thing that make the numerator equals to 0 is s equal to minus 2. So the zeros is at minus 2. So here we have the plot of poles and zeros on the S plane. So this is what we call in your MATLAB program is what we call PZ map, right? Pole and zero map on the S planes. So by now nothing complicated. So we have plot basically the poles and zeros of the open loop transfer. So next, second step. So we follow the step that we have mentioned previously. It is to determine angles from zeros and poles to the interested point. So what does it mean? So we have two poles and one zeros. What we want to determine now is the angles from these poles and zeros to the interested point. So what was our interested point? Remember the question? So the question was actually, the question asked us whether these points, 0, minus 3 is not 0. It was whether this point, so the point that we're interested in is minus 3 plus 0j. So this is the point. This is the point that we're interested in. The question was, is this point on the root locus? So if you want to determine whether this point is on a root locus or not, what we need to do is, in second step, determine the angles from the poles and the zeros toward the the point that we're interested in. So there will be three angles, right? So there are three angles that we are going to determine. So angle number 1. So let me erase that first. I don't think I need to erase that. I think everyone can see it. Right? So the first angle, theta 1. Theta 1 is basically, let's see at the figure. Theta 1 is the angle between these poles and the point that we're interested in. Let's say I'll call this point as point, how do you call it? As point A. I'll call it as point A. Let me get a pen. I'll call this point as point A. And then I'll call, so this pole is pole 1. So this pole is pole 1. This pole is pole, so they call it 3. And the zeros, they call it as 2. Right? So we need to determine the angles from the poles 1 zeros 2 and poles 3 toward the point A. So that's what we're going to do here. If everyone agrees and understand what we're doing here, so let's see what is theta 1. So theta 1 is the angle from poles 1 to point A. So this is the angle. So the angles have been here shown by this arrow over here. So this angle is basically 270 degrees minus the arctangent of this right triangle. So this right triangle, we see that on the j omega axis we have 3, the height is 3, and the base is basically 1. So it's arctangent of 1 over 3. So if we want to find theta 1, we do this calculation to find out that the angle theta 1 from poles 1 to point A is 251.57 degrees. So let's do for the other 2 points. For the angle of theta 2 is basically the angle between the zeros, the point 2, and the point A. So it is on the same axis, so the angle is basically 180 degrees, so no calculation needed. What about for the angle 3? Angle 3 is the angle between the poles, these poles, poles 3, we call poles 3. It's basically the second poles. The angle between it and the point A. So what is the angle? The angle is basically 90 degrees plus the angle in this right triangle. In this right triangle, the tangent of this small angle here is basically 1. So the base of the triangle is 1 and the height of the triangle is 3. So it's arctangent 1 over 3. And if you do the calculation, you have 108.43, right? So these are all the 3 angles from zeros and poles to our interested point A, right? Now that we have calculated the 3 angles from the poles and zeros to our interested point, what we need to do next is to determine the length of the vector from zeros and poles to the interested point. So what does it mean? Again, we have 3 poles. Let me give names just like what we had in previous slide. Get me a pen. So we call this pole, first pole as point 1, the zeros as point 2, and the second pole as point 3, and the point that we're interested in, which is basically 3 minus 3 plus 0j, as point A. We call it as point A, right? So what we want to do here, is basically to determine the length of the vector between these points of 1, 2, and 3, which are the poles and the zeros, to point A, right? So we have this vector that represent the first length, we call it L1, this vector which represent the second length L2, and this vector represent the third length L3. So we want to find the length of these 3 vectors. So let's calculate L1. So how do you find L1? So it's by Pythagoras. You see your right triangle, so you have both angles, both sides are at 3 and 1, so 3 square plus 1 square, square root. So the first length is square root of 10. Second one is easy, right? It's just 1. The distance between point 2 and point A is 1. And then the distance L3 is basically the same as distance L1. It's the same triangle, it's just upside down. So the distance is basically square root of 10. So now we have determined in point number 3, we have determined the length of vector from zeros and poles towards the point that we're interested in. So now the fourth step. The fourth step what we need to do is basically to check whether the condition and the properties of root locus is verified. So in order to do so, what we need to do is to add all angles that we have calculated previously. If it is equals to a multiple of 180, which is the condition, then it means that the point is on the root locus. So let's check. So our angles are theta 1, theta 2, and theta 3, 251.57, 180 degrees, and 108.43 degrees. So if you do the addition, so basically here you can basically it's a combination of them. Theta 1 here, what we do is basically to get 180 degree, it's combination of theta 1 minus combination of theta 2 minus theta 1 plus theta 3. Why do we have theta 2 minus theta 1 plus theta 3. Can anyone figure it out? So it is basically because we have our transfer function gs, we had numerator ns over denominator ds. And point number 1 and number 3 are our poles. So this is pole number 1 and this is pole number 2. And this theta 2, what does it correspond? The point on theta 2 is basically the 0. And the 0 correspond to the numerator, while the poles correspond to the denominator. So if you want to find the angle of the total function, it's basically the angle of ns minus the angle of ds. So the angle of ns is basically theta 2. That's why we have theta 2 minus theta 1 plus theta 3. So if we do the calculation, we get at the end is equal to minus 180 degree. So it is now verified that minus 180 degrees is basically minus 1 multiplied by 180 degree. So we verify the condition on the angles that the point that we're interested in, which is minus 3 plus 0j, is on the root locus. Right? It is on the root locus of our closed loop transfer function. Now that it is verified that it is on the root locus, the thing that we might be interested in is what is the value of k then? So that is the step number 5. So in step number 5, we can determine the value of k. So we know that the point minus 3 plus 0j is on the root locus. Now we want to figure out what is the value of k. To do so, what we do is we use the length of 0 and pole vectors. So we've done this in step number 3. So we have the three length L1, L2, and L3. They are square root of 10, 1, and square root of 10. So the condition on root locus, if the point is on root locus, k will be equals to 1 over the magnitude of the open loop transfer function, right? 1 over the magnitude of open loop transfer function. So this is basically 1 over the magnitude of the transfer function that we have calculated previously. So the magnitude, so what we need to do is, in order to calculate k, we need to do 1 over the magnitude of the transfer function. So what is the magnitude of the transfer function? Magnitude of the transfer function is basically what we need to do is, of course, again, the transfer function will have a numerator and denominator. It is the product of 0 divided by the product of poles. The product of 0, there's only one 0, which is 1. In terms of pole, there are two poles, this L1 and L3. So square root of 10 multiplied by square root of 10. That gives us a value of magnitude of 1 over 10. Right? So that is the magnitude m, 1 over 10. So in order to find k, what is k? K is basically 1 over the value of magnitude. So it's 1 over 10. So the value of k is at 10. So what we can conclude is basically that point of, let me take my pen back. So the point, if we have to conclude, the point minus 3 plus 0j is on the root locus of gs. So gs was our transfer function previously, the open loop transfer function, is on the root locus of gs with k equals to 10. So basically, imagine if you have, so this is S plane, right? So sigma j omega. There's a certain, imagine there's a certain root locus like this. What we were doing was basically we point a point, minus 3 plus 0j. We ask whether the point is on the root locus. So what we figure out is the point is on the root locus, and we want to know what's the value of k, because root locus is basically the tracing of the position of pole as k varies, k change. So the question is, what is the value of k? So this is the calculation, and we end up with k equals to 10. So yes, the point minus 30j is on the root locus, and the value of k when we are at point minus 30j is k equals to 10. So that is basically the application of the condition on the properties of root locus. So we have now understand the properties of root locus and how to, therefore in application, we now know how to check if a point is on a root locus or not using these properties. So that's all for this first part of root locus. We'll continue in another lecture video on root locus because what we have seen until now is basically, if we have to recap, we have understand the problem of root locus. I mean the problem of control system if we want to add a gain or a corrector. So we need to study it using root locus, and then we have also revised the basically the notion of complex number, vector in complex number, and then we have basically study the basic properties of root locus, and therefore in application how do we check if a point on a root locus or not. In the next coming subsection of root locus, we will study how to basically the plotting of root locus that we did previously was manual. We change value of k and we plot by one in the example. But in next lecture, we will study how to do it basically using several properties to make it quicker, and how do we define the sketch and refine the sketch as well. So see you in the next video lecture. Thank you very much.